Okay, so we are doing now, we are on section 8.7. We're talking about Taylor and Maclaurin series. And we did a few examples in our last class from section 8.7. And we ended on this example where we wanted to use multiplication of power series to find the first three non-zero terms of the Maclaurin series for this function. Now, of course, the Maclaurin series, if we were to use the definition of a Maclaurin series, we could get the first three non-zero terms, but the problem is doing that would involve taking some somewhat complicated derivatives. I mean, we can do it, but what we want to do instead, which is going to be easier, is to find the Maclaurin series for e to the 2x power and find the Maclaurin series for the log of 1 plus x squared power, and then multiply those Maclaurin series together. So we mentioned that, and of course, there is a handout that I made for you that includes some important Maclaurin series along with their intervals of convergence. This handout, incidentally, you'll have access to it on your final exam. On the final exam, there will be a thing, there's a feature called supporting documents, and I'll upload this document, this handout in that, and you could download it then on the final exam to use. Okay, now what are the Maclaurin series that we're interested in? The first one is e to the x power, and then the second one is the natural log of 1 plus x. So those are the two Maclaurin series that are of interest to us, and we're going to use those to get the Maclaurin series for e to the 2x power and the Maclaurin series for the log of 1 plus x squared. So, okay, let me go ahead here and go into the whiteboard. And, okay, one moment. So I'm going in the section 8.7 in the book too, here, where table 1 is, and that's where those series are. Okay. Let me just see here. I got to get the font right, class. Okay, so e to the x power has that Maclaurin series. So that means e to the 2x power, to find its Maclaurin series, all you need to do is substitute in 2x for x. Okay, and we can then get the Maclaurin series for e to the 2x power. And I can certainly simplify the series, and then I can write out some terms of the series. So like when n is 0, we would have a 1. How do we get the 1? That comes from 2 to the 0th power times x to the 0th power over 0 factorial, which is 0 factorial is 1. The next term would be 2x over 1 factorial. How do we get that? Well, that's 2 to the 1st power times x to the 1st power over 1 factorial. So, n starts at 0, and we count it up from there. And then we can just keep going. We can keep going. And I'm going to write out the first 4 terms of the series. Okay, and so this will be 1 plus 2x Since 2 factorial is 2, 4 divided by 2 is 2, so that's 1 plus 2x plus 2x squared. And then 3 factorial is 6, so that'll be, let me just, hold on class. I like things to be neat and organized, as you know, so let's try to be neat and organized. Okay, let's try her again here. One plus 2x plus 2x squared plus 4/3 x cubed. Okay, and that's the power series for e to the 2x. There's that power series. That's the Maclaurin series. Now the other Maclaurin series, well, the log of 1 plus x, based on the table, the power series for that starts at n equals 1 times -1 to the n minus first power times x to the nth power over n. So this implies then, you know, and I probably should have an applies up here. This implies that the log of 1 plus x squared well, we would just substitute x squared where the x goes. Are there any questions on this? All right, we could write this then a little more simply. This should be an n minus 1, sorry. Yeah, that's fine. That's fine. That's fine. So if we write out some terms, let's see. The first term is going to be a 1. No. First term is going to be a 1x squared because we're starting at n equals 1. So 1x squared and the next term is a negative x to the 4th over 2. Next term is positive. That would be x to the 6 over 3, and then so forth. Okay, now let me just check one thing here. Please let me know if you have any questions on this. Yeah, that's right. That's right. So now we have two Maclaurin series, and we want to multiply the two Maclaurin series together. We want to multiply this Maclaurin series by this Maclaurin series. And if we were to multiply those two Maclaurin series completely out, we would get an infinite number of terms, right? Because we would have a Maclaurin series for this function e to the 2x times the log of 1 plus x squared. But notice in the problem, they only want the first 3 non-zero terms. So let me show you then how we would do this. So let me go back to the problem here. Okay, and here we go. So in our solution now, what I'm doing is, I mean, really, I like this work up here, I've done, right? I've done that work. So in your notes, you could go really from here to here. So this is the Maclaurin series. 8,6 equals 4/3, by the way. This is the Maclaurin series for e to the 2x. And this is the Maclaurin series for the natural log of 1 plus x squared. Now to multiply the series, how am I going to do this? Well, I only care about terms of lower order. So I'm going to take the 1 and I'm going to distribute the 1 to the x squared. That gets me 1 times x squared. And then I'm going to take the 1 and distribute it to the term negative x to the 4th over 2. That'll get me 1 times negative x to the 4th over 2. And I could multiply the 1 also by x to the 6 over 3. But I'm going to choose not to do that because I only need the first 3 non-zero terms for this Maclaurin series for our function. So that would give me like a power of 6, a term that has a degree 6. I might not need that. So let me just stick to the lower order terms. Next, we'll take 2x. 2x will multiply the x squared. Okay, and then I could add more terms, right? But I'm going to stop there. Finally, I'm going to take hold on here, the 2x squared, and I'm going to multiply that by x squared here. And that gets me 2x times x squared. So you see what happens is if we add up just the 4 terms you see, okay, so like 1x squared gives me x squared. 2x times x squared gives me 2x cubed. 1 times negative x to the 4th over 2 plus 2x times x squared will give me 3/2 x to the 4th. Because negative 1x to the 4th over 2 plus 2x to the 4th, that's what 2x times x squared is. That is going to give me 3/2 x to the 4th. Now I can find other terms in this product of the 2 series, but those terms are going to have degree 5 or more. Okay. And I'm not worried about those because I only want the first 3 terms, first 3 non-zero terms. So we can say then that e to the 2x times the natural log of 1 plus x squared is equal to x squared plus 2x cubed plus 3 halves x to the fourth plus dot, 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 dot. But WebAssign is going to want you to enter in those three, that part. So this is how we can find a Maclaurin series for a complicated function. If the function is a product of two other functions that we can get the Maclaurin series for, we can just multiply those Maclaurin series and judiciously write down terms. And you can also do that for functions that are like quotients of other functions. You can find Maclaurin series for products of functions or quotients of functions. And example 13 in section 8.7 talks about that a little bit. So that's a nice example to look at as well. Because they have one where they find the Maclaurin series for the tangent function. And they take the sine, the power series for the sine, divided by the power series for the cosine. And they show how to divide those power series and come up with a Maclaurin series for the tangent of x. So that's example 13, section 8.7. So you'll want to look at that too. Are there any questions before we move on? Okay, well, let's go ahead and look at another example here from section 8.7. I'd like to look at one more. Let's do something with an integral. So let me give you a moment to copy this example down. Okay, so in this problem, we have an integral of the arctangent of x cubed plus the sine of x cubed. Now, does anyone offhand know the antiderivative, for instance, of the arctangent of x cubed? I certainly don't. Does anybody know I'm sorry, I'm not saying this right. I'm sorry. Does anybody know the antiderivative of the arctangent of x cubed? I certainly don't. And the antiderivative of the sine of x cubed, I don't know what that antiderivative is either. And probably there is no formal antiderivative. And so when you're encountered with these kind of situations, you're trying to find, you're trying to evaluate this integral. You need to then replace these functions with their power series. So you learn how, it's from section 8.6, how to do the integral of a power series. So if we can find the power series for the arctangent of x cubed and the sine of x cubed, we can substitute in those power series or Maclaurin series for those functions and finish the problem. So first, what we want to do is, of course, refer to the table. And remember, this table, that my handout is, if you go to Blackboard and look under the course content folder, go to chapter 8 and find section 8.7, you will see there's a link to download this handout. Okay, so I don't know, has anybody tried that yet? Has anybody tried that? Maybe not, since you're focused on your fourth exam, but it's there. It's there. So, okay. So, well, all right. We have the arctangent of x cubed. So we're going to need to use the Maclaurin series for the arctangent function to help us. And then we have the sine of x cubed. So we're going to need the sine function to help us. So just like in the previous problem, we can use the Maclaurin series for the sine and the arctangent to find Maclaurin series for the sine of x cubed and the arctangent of x cubed. So, okay, let's go ahead to the solution here. So this is the Maclaurin series for the arctangent of x. And, don't worry about interval of convergence. I mean, the integral is defined from 0 to 0.2. And the problems are such that the limits of the integral fall within the respective intervals of convergence. So there's the arctangent of x. Well, based on that, we can find the arctangent of x cubed. We can find its Maclaurin series. And similarly, the sine of x, and I'm going to give you a chance to copy this. The sine of x has that Maclaurin series, and based on that, we can find the Maclaurin series for the sine of x cubed. So I'm going to let you copy that. And please, I don't think I need to spell out every detail here. You've done this kind of thing before. Let me just let you copy it down, and please let me know if you have any questions. How many are feeling good so far with what they're seeing here? We haven't finished the problem yet, but so far so good. Maybe give me a few thumbs up if so far you're okay, you're comfortable. Okay, Taj is and David is. Good. Good. So naturally, we need to get these Maclaurin series in their most simplified forms, right, in order to really work with them. And that's what we've done. And now what we want to do is take these Maclaurin series and substitute them back into the integral. Okay, so if you're good with that, I'll move on here. Okay, well, let's substitute these Maclaurin series in the integrand. So here we are. There is the arctangent of x cubed and the sine of x cubed, and I'm substituting in the corresponding Maclaurin series. Now we note on this step here that we have an integral of a sum. Well, an integral of a sum is the sum of the integrals. So that gets us down to here. Now, when you take the integral of a power series, you're taking the integral of a sum. Well, an integral of a sum is the sum of the integrals. So we can rewrite these two integrals as you see in this step here. So hopefully you've done this kind of thing in section 8.6. You've seen this. You've seen how to work with integrals of power series from section 8.6. So hopefully everybody's comfortable to hear. Let me know though if you're uncomfortable. And now remember, we're integrating with respect to x, so that means -1 to the nth power and 2 times n plus 1. We treat that like a constant. So that constant, those constants can be pulled out in front of the integral. Same thing over here with -1 to the nth power and 2n plus 1 factorial. Those are treated like constants. They're not dependent on x, so they can be pulled out in front of the integral. And then you do your antiderivatives for x to the 6n plus 3. And that's just x to the 6n plus 4 over 6n plus 4. And then you have, of course, constants of integration, because these are indefinite integrals. So you have a C1 and a C2. What we found now down here is we found a power series representation for the antiderivative of the arctangent of x cubed plus the sine of x cubed for a certain interval of convergence, of course. But that's pretty cool to be able to take an indefinite integral and express that indefinite integral as a, well, in this case, it's the sum of two power series, right? Pretty cool. Now, what you might notice is both of these power series start at the same index, at n equals 0. So because they both start at the same index, n equals 0, what can we do with those two power series? They both start with the same index, n equals 0, same starting index. That's right, Taj. Therefore, we can combine those two power series. Now, if one of the power series started at a different index, we'd have to convert that power series so it would start at the same index as the other power series. You've seen how to rewrite power series with a different index. It's possible to do. And like in differential equations, it's done all the time. You'll be using power series to find solutions of differential equations in Math 282. For here, though, we're just concerned about, hey, we can combine those two power series. And of course, the constants of integration, we could combine those two into one constant of integration. So I'll do that. Are there any questions before we move on to the next page? Okay, well let's proceed on then. I'm trying to make sure I'm pacing myself okay too. Let me know if I'm going too fast. Okay, well on to the next page. So here we are. I'm going to combine the two power series here. I'm going to add them to get this power series. And incidentally, for that single power series, it appears we have a common factor. Well, we actually have a common factor of -1 to the nth power times x to the 6n plus 4 divided by 6n plus 4. So there's the common factor. And I can rewrite the power series as you see here. It just makes life a little easier if we rewrite the power series in the most simplified form possible. So our indefinite integral here equals this power series. And we can use that power series to evaluate the definite integral. Okay. Absolutely. I mean, how many think offhand this is really pretty cool? Okay, Taj is liking it, and Ange is liking it. Notice that we have here an alternating series because we have a -1 to the nth power as part of our power series. So when we go to estimate this definite integral correct to 5 decimal places, because we have an alternating power series, we can utilize the alternating series estimation theorem. Okay, and I'll show you that. So are there any questions before I go to the next page? Okay. All right, so now it's time to find, to evaluate our definite integral. So the definite integral goes from 0 to 0.2, 0.2. And I'm just going to substitute that in for x in my power series. So x would go in, 0.2 would go into x, and then 0 would go into x. If so, like, you know, just like when you evaluate a definite integral, the top limit goes in first, minus the expression or the antiderivative with the bottom limit. Well, the bottom limit is 0. If we put 0 in for x, we're just going to get a big old 0. Every term of the series would equal 0. And so that leaves us with this as our series. So we're going to add up terms of a series to estimate the definite integral. Add up the term of that series. But remember, we want to have the series correct, or our definite integral, our estimate, we want to be correct within 5 decimal places. Well, that's equivalent then to saying, let's check to see that our, you know, let's add up enough terms of the series until we're assured that our that the terms of our series, the sum of them, will give us an estimate correct to 5 decimal places. So we're going to use the alternating series estimation theorem. So 5 decimal places. So as you know, we always have a 5 in the numerator when we say correct to a number of decimal places. There's a 5 in the numerator. And since we want correct to 5 decimal places, we're looking at in the bottom of 10 to the 5 plus 1 power. So that's 10 to the 6th power, 5 over 10 to the 6th power. Well, the first term here is equal to 0.0080. That's greater than 5 over 10 to the 6th power. But the next term here, okay, we won't worry about the negative for the moment. The 0.2 to the 10th power over 10 times 1/3 plus 1 over 3 factorial, that's going to equal 0.000000, sorry, hold on. How many zeros do I have there? Let me check here. 1, 2, 3, 4, 5, 6, 7, 8. Looks like 8.00000000512. And that's certainly less than 5 over 10 to the 6th power, because 5 over 10 to the 6th power is 0.000005. And so that means then that we only need to get our estimate correct to 5 decimal places of this definite integral, we only need one term of the series by the alternating series estimation theorem. Are there any questions? Any questions at all about this? Okay, so all this of course, this is extremely important for your final exam, what you're learning here in section 8.7. I mean, this is, and well, now let me then, if we're good with this, I'll go ahead and summarize the rest of the problem. I mean, we're done basically. We can say then, by the alternating estimation theorem, that our definite integral is approximately equal to the first term of the series, which is 0.2 to the fourth power over 4 times 2, which is 0.00080. I mean, we only needed, in this case, one term of the series to get that level of accuracy. And in fact, that term is actually correct to 7 decimal places, because the second term of the series, disregarding the negative, second term of the series is actually less than 5 over 10 to the 8th power. So we're actually, like, this estimate of the definite integral, 0.00080, is correct to 7 decimal places. So it's pretty darn good. And of course, it's just because of the nature of the problem. But yeah. I mean, this is truly, I think, some of the most beautiful mathematics that, well, I mean, all math is beautiful. There's different kinds of beauty, but this is truly beautiful. And, this is not something like at the beginning of the semester you would have been able to really, I think, do, right? Because you have to have more calculus knowledge and mathematical maturity. But now you have that mathematical maturity. I mean, you're almost ready to move on to our higher level math classes. And that's how this problem works. So I think now, given the examples we've covered in section 8.7, between today's class and your last class, I think you have a good representation of problems. The book, of course, has excellent examples, and example 13, you'll want to look at that as well. Are there any questions before I stop the recording? All right, who's reasonably good with this? I mean, I know it's going to take time you have to work on the homework and all that, but initially, are you okay with it? Maybe give me a thumbs up if you're okay, somewhat comfortable. Okay, Ange is, Taj is, Mario is, okay, all right. Okay, great. All right, well, let me go ahead and stop the recording here.